See this image. What do you see? One galaxy at the center and four galaxies at the outer edge. Nothing extraordinary, right? Now listen carefully. The galaxy at the center is 400 million light years away, and the outer galaxies are 8 billion light years away, which means 20 times further away. Now, it seems a little odd, but the story doesn't end here. The outer four galaxies are just reflection of a distant quasar, and this image is very famous by the name Einstein Cross. At this point, many questions are coming in your mind, right? Let's see one more picture. It's a perfect Einstein ring. Do you know how and why this ring structure has formed? There are many images of space where you will see these half-ringed or full-ringed structures. These are very common in space. It may seem strange, but long ago when these pictures was a dream for humanity, Sir Albert Einstein predicted these structures. But how is it possible? Don't be so confused. I am here to answer all of your questions. Today, we will discuss one of the most strange and peculiar phenomena in space, the gravitational lensing. Hello everyone, my name is Aditya and welcome back to my YouTube channel, SkyMap. In 1919, the great astronomer and physicist Sir Arthur Eddington observed the star's placement around Sun during a solar eclipse. He witnessed a unique problem. The placement of stars around the Sun had shifted a little bit, but when the Sun changed its position, the stars came back to their original position. Later, this news gained popularity through the New York Times. But what is the main reason behind it? In simple words, the light coming from the distant stars is bending due to the high mass of the Sun. Light can bend if it passes near or through a huge mass. In our school level physics book, we learned that light always travels in a straight line. Is it not true on a universal scale? We usually see our space in three-dimensional scale. But according to the general theory of relativity by Sir Albert Einstein, it's originally four-dimensional. The fourth dimension is time. The best way to understand the four-dimensional space and gravity is by assuming a space-time fabric. Imagine a space-time fabric and the stars, planets and galaxies are just placed on it. Now, whoever has a mass will create a bend downward on the fabric. When the mass increases, the curvature of the bend increases. And as the curvature increases, time starts flowing more slowly. In the extreme condition where the mass reaches infinity, the time will stop flowing for the object. It's the condition of a black hole. Now, when the mass and curvature simultaneously increases, it attracts more and more objects. According to the theory of relativity, this attraction is called gravity. Let's come back to our topic. In our universe, there are many galaxies and galaxy clusters. These objects with huge mass bend the space-time fabric. When light travels through these high-mass galaxy clusters, it actually travels through the curved space-time. Due to this curved space, the light bends. So our school level physics book is correct. The light doesn't bend. It's the light's traveling path, the space, that bends. As a result, it seems like the light bends. It's called the gravitational lensing. Let's take the example of Einstein Cross. These four outer galaxies are actually a quasar 8 billion light years away and magnified by a nearby galaxy. This phenomenon is very common in our universe. It's so common that nowadays scientists use this method to see distant objects in space. Now, see this image. This one is a perfect reflection of a candle. It happens when the alignment is perfect. But when the alignment is out of focus, see what happens. It creates distorted image. In the space, what we see is not always a perfect alignment. Sometimes it comes in a straight line and produces this type of image. But when it doesn't come in a single line, it creates this type of distorted image. With extended studies, nowadays scientists can even identify objects from these pictures. Let's take a closer look at the famous discoveries by the gravitational lensing. And trust me, there are many. This is the image of a galaxy cluster named WHL013708. You can see many gravitational lensing effects in this image. But what makes this image special is this one. It's called the sunrise arc. Why? Because this is the farthest star discovered by humanity. Its name is Earendel. In Old English, Earendel means the morning star or the rising star. The star came into existence within 400 million years of the Big Bang. This means this starlight is traveling almost from the beginning of our universe. The light you are seeing has traveled 13.4 billion light years to reach us. The star came into existence long before the formation of our own Milky Way. Just due to gravitational lensing, today we have witnessed the sunrise arc. This is another galaxy cluster. You can clearly see lensing effect. This magnified galaxy is a distant galaxy behind the cluster. The interesting fact about this lensing effect is in the year 2016, Hubble observed 3 new stars. Later, in 2019, Hubble confirmed these 3 stars has vanished. Again, in 2023, James Webb confirmed another 2 new stars. So what is going on? According to scientists, these dots are not stars. It's actually a rare event called supernova, occurring in the distant galaxy. When a massive star reaches the end of its life, it explodes with a big explosion. It's called a supernova. To know more about supernova, please watch this video. Back to our topic. Due to magnification, we can see the light of the supernova explosion. Considering the distance from the galaxy, it is not possible to see the rare event without this lensing effect. Calculation shows in the year 2035, once again the light will reach Earth. A similar incident occurred with this image. Here, scientists observed 4 reflections of a single supernova by gravitational lensing in 2014. Later, they predicted that one more light from the same supernova was yet to arrive. According to the prediction, in 2015, they observed another light from the same supernova. These dots are reflections of the same supernova that arrived Earth at different time frames. This occurred because the light had taken different paths due to different lensing effects. When lights from a single light source hits Earth in different time frames due to different traveling paths, it helps us to calculate the expansion of space. So, gravitational lensing is a natural magnifying process that helps us to study our universe more closely. Most of the galaxies in the early age of our universe with redshift greater than 10 has been discovered by this natural magnifying process predicted by Sir Albert Einstein. In honor of his insane contribution, we have named the most precise and accurate lensing effect after his name, the Einstein ring and Einstein Cross. Lastly, let's talk about the discovery of dark matter using gravitational lensing. I think you have understood that in gravitational lensing, the light bends due to the mass of the intermediate object. Indirectly, by back calculation, scientists can also calculate the mass of the intermediate object by measuring the amount of bending of light. When they did so, the mass didn't match their observation. The galaxy clusters with thousands of galaxies doesn't carry as much mass as it need to carve the light in this pattern. So, there must be a huge amount of mass present that is invisible, and this hidden mass is responsible for the gravitational lensing. Surprisingly, this invisible mass is almost 85%. This invisible matter is known as dark matter. We don't know much about dark matter. The study is ongoing. Till today, it is one of the biggest mysteries of our universe. To learn more about dark matter, I highly recommend you to watch this video. So, the bending of light is impossible. But if the light's traveling path bends, it seems like the light is bending. People think light bends in gravitational lensing, but it's a big misconception. If you have understood the concept, then one last question to you all. If time slows down due to huge mass and space-time curvature, then how does this time affect the light's traveling path? Will it slow down the light's speed? How will it affect gravitational lensing? If you know the answer, please write down in the comment section. I would love to know your thoughts. If you found this cosmic journey fascinating, then I think you will also like this video, where we have unveiled the mysteries of black hole, where space and time doesn't exist. Lastly, please don't forget to give this video a thumbs up, share it with your friends and family members, and subscribe for more space related content. And remember, keep looking up, stay curious, and explore the mysteries of the night sky.